Good evening, everyone. I would like to extend my warm welcome to all of you to the fourth day of the session, especially our honorable guest, Dr. Neethu Roy from MBCET and Dr. Asif Ahmed from Ingevity. Today's session is scheduled as follows. From 7 to 7:50, we have a talk on HME material characterization by Dr. Neethu Roy. The next 10 minutes is reserved for discussions related to the topic. From 8 to 8:50, Dr. Asif Ahmed will be delivering a talk on the options, challenges, and current practice in hot mix recycling, which will again be followed by a 10-minute query session. From 9 to 9:30, a detailed interaction session is scheduled. Now, I would like to welcome our distinguished guest, Dr. Neethu Roy from Mar Baselios College of Engineering and Technology, Trivandrum. She is currently working as a professor and research and consultancy dean at MBCET. She did her bachelor's and master's at College of Engineering Trivandrum and secured her PhD from IIT Madras. Her areas of interest include payment material characterization, analysis and design of payment systems, and payment management systems. With great pleasure and honor, I invite Dr. Neethu Roy to have a talk on HME material characterization.
Yeah. Am I audible?
Neethu.
Yes, ma'am. Good evening, ma'am.
Good evening.
So I think my screen is not in slideshow mode. Okay, one second. Is it in slideshow now?
Yes, it is.
So can I start? Hello?
Yeah, yes. Just next slide. Can you show this slide? Check whether it is moving. Yeah, yes. It's working.
Okay. So very good evening to one and all. First of all, let me thank Dr. Tushara and Professor Ashalata for giving me this opportunity to participate in this FDP and give a session on fatigue and rutting characterization of bituminous mixes with RAP. Okay, so for the past couple of days, we have been listening to various sessions on this material, which is RAP. And you want to use this material, which essentially is valuable material in the payment construction. You have seen how Professor Murali has already discussed on how this characterization need to be done. And Professor Nevita, yesterday I heard her talking about the RAP binder characterization, and Professor Padma already discussed about how we can evaluate a modulus value for this material, right? So in this lecture, what I am going to discuss is about how we characterize the distresses or the distress related properties of this RAP containing mixture or the HMA with RAP. Okay. So moving on, I have taken some pictures and photographs from various Google sources. So my acknowledgement to all those sources, I might not have cited them in the slides. Okay. So a quick background. As we know, as we already being discussed here, is that you have RAP, you add certain new materials to it, some virgin aggregate, some bitumen, rejuvenators. So you prepare a mixture, right? You have a mix design formula, or you try to arrive at certain mix with the assumption that it will perform in the field. Now, what is this performance you are looking at? You are looking at majorly three performance in terms of three aspects. One is rutting, second is fatigue cracking, and the third one is low temperature cracking. As far as a country like India is concerned, we are not very much concerned about a low temperature cracking. So the major distresses that we will be concerned about is rutting and fatigue cracking. Okay. Now, how do you study about the performance of a payment structure? Essentially, there are various ways. Like the first and the foremost, or the most typical or the correct way of doing it is that you should go observe your payment structure for years and see how it is performing, right? So you can have in-service payment studies, wherein you see what is the actual loading conditions, what is the actual environmental factors, what is the actual construction, the layer thicknesses, the quality of construction, everything varies from site to site. And in order to get the correct information, you have to go and do a site study. Now, if it's not possible, you do some test stretch studies, right? You are aware of it, I'm sure. You have, see, this is an NCAT test track, wherein you construct the test track, the actual payment structure, with the kind of materials you want to explore, with the kind of thicknesses, with the kind of layers and all, and you will load it with a known load quantity and known load factor, loading, which will be continued for a couple of years or a couple of months, and you collect all the possible informations regarding how this payment is performing. Now, even if this is not possible, you go to an accelerated loading facility. Okay, you see that you can construct a small stretch of structure or your payment, then you do an accelerated loading, to and fro loading kind of thing, and again you collect information about the performance. Now, all these are typically the data regarding the flexible payment as a whole, or a bituminous pavement as a whole, right? Now, if you want to study about the top layer or that bituminous layer that we are concerned about, see, you can have accelerated testing in the laboratory, which you call like a wheel tracker test or a accelerated flexure test on the material. So that forms the performance evaluation of the mixers in the laboratory. Now, how are they differ? So as I already mentioned, if it is an in-service payment survey, you see that your loading is random, your environmental conditions are random, and the time period required for collecting this data may go from 3 to 4 years, because all these damages that you see in the field doesn't happen overnight, right? It will take a lot of years to accumulate and see, propagate and see on top of the surface of the payment. So it takes a lot of time, and you can, in such in-service payment studies, it will give you a lot of information on the various causative factors for responsible for the rutting and fatigue cracking in the field. Whereas in the case of test tracks, I'm sorry about that. 1 second, if you don't mind. Hello. Yes, sir. Thank you. I'm sorry about that. So in the test tracks, it is a controlled condition where the loading is controlled. As you know, the loading that it moves on the top on the test track is known factor for you, but the environment is random, but you can measure what is happening during the period of study. In a few months, you can collect information regarding the distresses. Now, the third is, as I said, the accelerated loading, where you can have the atmosphere or the environmental conditions as well as the loading in a controlled condition, and within a few days will give you some sort of an information, right? Now, so what I'm going to discuss here is the performance evaluation of your HMA mixes or with RAP in the laboratory for rutting and fatigue cracking. Okay. Now, what are the factors that you need to consider? You need to consider, or you are essentially trying to mimic what is happening in the field on these test specimens and try to test them. So as far, there are a lot of test procedures that are being developed. So what I will be discussing here is the 3 major tests that are used normally for characterizing the rutting potential of bituminous mixtures. One is the flow time test, and the second is a flow number test, and third one is a wheel tracker test. Okay, and as well as the fatigue cracking characteristics of this material is concerned, we will look at what is the 4-point flexural beam test and what is a semicircular bending test. So all these tests are laboratory scale tests which can be conducted in a couple of hours of time, which is supposed to give you some information on how it is performing in the field, or there should be some way to correlate that information to the field response. So let us look at the rutting characterization of HMA mixtures. Now, I'll be using the term HMA mixtures because RAP is something which is being added to the HMA mixture, essentially to act like an SMA mixture. So there is not any specific test procedures or protocols for the testing of these mixtures, RAP mixtures as such, because all of the test procedures that are being developed for HMA mixtures will be utilized for the RAP characterization RAP HMA mixture characterization as well. Okay. So let us talk about the rutting of bituminous pavements first. See, if you see a rutting on top of a pavement surface, it could be due to the rutting in various layers, right? It could be rutting on the top bituminous layer alone, or it could be rutting at different layers of the pavement structure. Now, how do you know what rutting it is? See, there are ways in which, based on long-term pavement performance studies that are conducted at various places, they have identified that if you observe something like this, a surface pattern like this of rutting, you can say that it is a surface failure, because at two wheel paths you see a depression and there is humps formed on either side of the depression. So this is a surface profile essentially. Okay, and if you see a hump in between and there are two depressions along the wheel path, you can say that it is due to the base layer which has failed. Or if you see like one deep rut on that surface, including both the wheel paths, you can say that it is like a subgrade failure. Now, how do you get all this information? It is from field studies. Okay, so let's look at what IRC talks about this rutting, or how this is being tackled in the pavement design aspect. See, this is a typical pavement cross section. All of you are aware of it. This is the IRC 37 design code, which shows a typical cross-section of a pavement structure with the subgrade and the granular layers, which are the base and the subbase, and you have the bituminous layer on top. The bottom bituminous layer is marked here as a fatigue resistant layer, and the top one is written as a rut resistant layer. Okay, so here the distress transfer function for rutting that is given in IRC 37 is this, which is NR is equal to some constant, and it is related to epsilon B. Now, what is this epsilon B? It is the vertical compressive strain on top of the subgrade. Right. So what you are looking at, how do you get this information? Again, this is based on the pavement structure evaluation, structural evaluation of the pavement based on layered elastic analysis. You see what is the vertical compressive strain on top of the subgrade. You can now plug it in here to get the number of repetitions to failure by rutting. Now, what is this failure by rutting? IRC essentially says that if you see an average rut depth of 20 mm, that is designated as failure due to rutting. Okay, so in this structural evaluation of pavement as per IRC, we are essentially looking at the subgrade rutting. Okay, or you're looking at the strain on top of the subgrade. So it essentially talks about the subgrade rutting. So you are interested in minimizing the subgrade rutting, which minimize the rutting on the top of the pavement surface, is what the idea is all about, right? So what IRC suggests is that if you look at the bituminous layer alone, you try to make it as a rut resistant layer. You can work on your mix design, you can work on your performance characterization of the material. You use better material, different construction approaches. You arrive at a mix that will be rut resistant. So this is what the whole idea of pavement design as far as IRC is concerned. Okay, so so it is our responsibility to see that that mixture that you put on top is essentially rut resistant, right? So moving on. So with this background, let us see how this performance is characterized, or the rutting performance is characterized in the laboratory for bituminous mixtures, and without RAP or with RAP. Okay. So the first test, as I mentioned, is called a flow time test. So what you're doing is that you will prepare a cylindrical specimen of your mix and you apply a constant creep load. Okay, so just like if a truck is being stationed on your pavement surface, how it performs, like that you want to try on this bituminous material how a creep load will create a response. So you see here, this is a stress. It is a constant stress. Normally, you apply a a seating load will be given so that the load will always be in contact with the specimen. So so first give a seating load, and then the deviatoric stress or the creep deviatoric stress is given. Now, when you apply a stress like this, essentially the specimen starts deforming, or you can measure or you can compute the strains. Okay. Now, the creep strain typically follow a 3-stage response like this. Essentially, there is a primary stage, there is a secondary stage, and a tertiary stage. What you see is the rate of strain is at a higher level, or it keeps on decreasing at this level. Then it becomes a constant. The rate of creep becomes constant, or you can see that there is a straight line portion there. And then again, the creep strain starts increasing at an increasing rate. So this is called the tertiary region. Now, when a material response is like this, you see that when the tertiary stage is reached, it starts to flow, or the material has failed by rutting. So the beginning of the tertiary stage is actually denoted as the rutting failure, or that time which corresponds to beginning of the tertiary stage is denoted as flow time. Okay. Now, what are the test conditions that is specified for flow time test? Normally, you can do the test at a 4% to 6% air void specimen. Now, why 6% and why 4%? You know that when a bitumen layer is laid and compacted, its temperature, its air void is of the order of 6 to 8%. Suppose you want to mimic what happens right from the laying of the, or the, right from the start of the age of the pavement, the bituminous layer, you can compact it at 6% or 8% and see how it performs. Or if it over a period after this shakedown kind of thing has all or that consolidation has the compaction kind of thing has completed, when it has reached the 4% air void, you want to measure the rutting from that basis, you can prepare the specimen at 4% air voids. Now the temperature normally from you can go from 25 to 60% based on what temperature you are looking at. Essentially it will be a high temperature because this is a phenomenon happens at high temperature. And another aspect is that you can test the specimen at a confined condition and an unconfined condition. Now what is this confined condition? Your specimen, if you look at any point beneath a certain inches below the surface of the pavement structure, you know that it is subjected to a triaxial state of stress, right? So while you are testing it also, you essentially want to test it at this triaxial kind of test. So you can apply a confinement pressure on the specimen and then the deviatoric stress, which will be the load that acts on the top. So these are some of the values that are given, or the suggested range of values wherein you have to test the specimen. And again, you don't have to go by these values because considering the temperature and the type of the specimen, some may be performing or some may be you will be able to do the test at these ranges of loadings and confinement conditions, and some it may not be possible. So you have to these are not standard values. That's what I want to mention. Okay. Let me just quickly show you how the specimen is being prepared. So this is essentially the specimen of 100 mm diameter and 150 mm height. You can prepare it in a gyratory compactor and core it and slice it and get the specimen of such a finished shape. Okay. Or you can have a press box specimen and then core from this press box specimen and get these specimens. And you need to attach, essentially you are trying to measure the deformations. It has to be measured at different points, or at least 3 points on the specimen, and then averaged it out so that you will get the exact correct representation of the deformation. So normally 3 LVDTs are used on the surface. You see here. Now the LVDTs will be connected by using at a particular gauge length using studs. So you see here, this is a way in which you can attach the studs to the specimen, and then this is the attachment to which the LVDTs will be connected, and this is how the specimen is kept inside the temperature controlled chamber of a asphalt mixture performance tester, or AMPT. So this is your AMPT. You have the thermal controlled chamber inside which you see that there is a specimen which is being tested in an unconfined condition. Now, if you want to apply the confinement, you have to cover it with a membrane. Otherwise, air will not provide the pressure on the specimen because it is an it contains voids. So you attach or you put it inside a membrane and then you attach the LVDTs and test it. Okay, so this is how you do and this is by on top through from the top you apply the creep load and then the deformations will be measured. All three strain gauges will measure the deformation, right? So this is how a flow time test is conducted. Now let me quickly go to the flow number test. Ideally, the arrangements is more or less the same. This is the specimen casting, the preparation of the specimen, everything is or the arrangement of the LVDT is all the same. But this is a test being followed. Nowadays, we don't follow the flow time test. This is as per the ASTRO T378 protocol. You want to apply rather than a constant creep load, you want to apply a repeated load. Okay, so the load cycles are, you can see here, the load cycles is shown here. It is a Haversine loading of 0.1 second duration and a rest period of 0.9 seconds. Now, why you need a repeated loading? You want to mimic the traffic loading, the loading that happens if a moving load comes, it will start loading a particular point and it will keep on increasing loading, and then when it moves away it will decreases. So it will be like a Haversine pulse. You can consider it as a Haversine pulse, and the next axle comes. This time denotes the rest period between the next axle comes. So, okay, so essentially 0.1 second and 0.9 second duration will represent the passage of one wheel load. So the loading as well as the rest period as actually happening in the field is in a way mimicked when you consider this 0.1 second, 0.9 second, 0.1 second loading and 0.9 second rest period kind of a loading. Okay, so here also a seating load is given, and also the test can be conducted at a confined condition or an unconfined condition. And what happens when you load it? The deformation increases, and when you unload it, the deformation decreases. There will be a recovery of the deformation, but it will not go down to zero. Why? Because there will be a certain amount of permanent deformation, because you are talking about viscoelastic bituminous mixes, right? So there will be certain amount of irrecoverable deformation there, and after the second cycle, third cycle, this keep on accumulating. So you can see here, after the first cycle, at the end of the rest period, there will be certain amount of irrecoverable deformation which keeps on accumulating. So here also you can keep on measuring this irrecoverable deformations and you plot it. So this will represent the repeated creep, permanent deformation or the permanent strain with respect to the number of loading cycles. So at every loading cycle, you have noted down the D, what you have measured here. This is as D. Okay. So this also is expected to show a 3-stage creep response, wherein you will have a primary zone, then you have a secondary zone, which is more or less stationary, a steady state, and then it goes to the tertiary zone. When the tertiary zone starts, you call it as that number of cycles corresponds to the flow number. Okay, I hope this is everyone is clear about this. Again, what are the test conditions? And say the ASTRO standards tells you how to prepare the sample and what are the test conditions. Essentially, the mix has to be made and it has to be conditioned. That in the flow time also, you have to condition the mix. A short-term conditioning as per R30 has to be done 4 hours at 135 degree. You prepare the mix and spread it and keep it in the oven for 4 hours for the initial conditioning of the mix, and then you will prepare the specimen in a gyratory or a press box compactor. Essentially, the code suggests a zero test under unconfined conditions, but it is also suggested that if possible, it need to be conducted at different confinement conditions and see how the material responds. Okay, the axial stress suggested is of the order of 600 kPa with a contact stress of 30 kPa. Now, till what time you will do this test? You can keep on continuing this number of cycles. At least 10,000 cycles are to be done, or until the specimen fails by excessive tertiary deformation, or at least 5% of the plastic strain or strain has reached 5% of plastic strain has reached, or the irrecoverable strain has reached, because you actually want to see when the tertiary state starts, right? So that is an indication of the rutting response of the material. So you want to load it in such a way that it will go to that tertiary stage or the starting of the tertiary stage. Now, what are the temperatures at which you test? You can test it at like all the higher temperatures possible. This AMPT gives you a capability of testing up to 60 degrees Celsius. So in certain studies, we have conducted it at 40, 50, 60 temperature. Okay. Now, once you capture this data, now we have to post-process this. I have mentioned that this is starting of the tertiary stage is what we are interested in. That is that one number we are interested in, which is your flow number, right? So how to get it? Now you may find that, okay, it looks very simple. You can directly get it from there. But the problem is that this is a kind of test, mixture test. There will be a lot of noise in the data. It will be very difficult for you to precisely find out what is that one point where the tertiary zone has started. So there are various approaches by which we post process this data. Let us see the first one. This is like a smoothened approach. What you do is that you find a rate of change of this strain. Okay, so your strain, you see here, this pink line indicates the strain, and you take the rate of strain, rate of change of strain, and then you smoothen that curve and essentially draw it. So you can see that the rate decreases and it reaches a minimum value, and then it increases. Now again, you can pick what is that minimum point that will correspond to the flow number, right? But again, the problem is that this will have a lot of noise in it. It may not be able to find one point. Like you will find there are a lot of local minimum points may happen. So there is like some 5-point averaging will be done. So this is essentially an averaging technique. You are taking the first point, next 2 points to the left, 2 points to the right, and take an average of all the 5 points. So likewise, you can do a 5-point average and smoothen it, and try to get the lowest point. Okay, so that's a rate where it has become the minimum, right? And the second approach is that rather than smoothening the curve and trying to find it, you can fit some models to this data. So the Franken model is one such approach wherein they essentially see that, okay, this 3-stage curve can be represented using a power model and an exponential model. Okay, so this is the typical model with the first term indicates the power equation, and the second term indicates an exponential equation. A, B, C, D, etc. are the coefficients. So you can just fit it. Then you can take a rate first derivative, or you can take a second derivative as well. So from the first derivative, we can see that whenever it this first derivative becomes 0, you can say that you have, okay, that the first derivative becomes 0. You can say that it is the flow number, corresponds to flow number, or you can take this rate of change of slope. That slope indicates changes sign. Okay, either the slope when it becomes 0, or when the rate of change of that slope becomes positive to negative, you can say that that point represents the flow number. Okay, this is the second approach. And the third approach is that Zhao has identified that it is not just a power law and an exponential law. There is some portion in between which can be indicated by, or which can be represented by, a straight line. So he has represented it with a 3-stage model. You see that there is a power law model, then there is a straight line portion, and then there is a exponential model is added. So this is a 3-stage. So you can use this data and fit these 3 models and see where the exponential part starts. Okay, so that particular point denotes the starting of your tertiary stage, or essentially your flow number, right? Now, you can conduct this test on the mixture, but will you always get such kind of a very smooth and very beautiful 3-stage curve? No, because these are some of the studies that we have conducted using normal bituminous mixtures, BC grade 1. This is not containing any wrap, but what we have observed is that even for that type of mixes, you could get, based on the based on the condition of testing, we could get different types of curves. Like for example, this is like we named it as like type 1, 2, 3, 4, etc. You see a type 1 curve wherein all the 3 stages of primary, secondary, tertiary was very beautifully shown, whereas in the type 2 it was essentially in 20,000 cycles. We have reached up to 20,000 test cycles. It was still in the primary stage. Okay, and the third one was that it was in the primary and a secondary stage. Though these look identical, it's actually primary plus a secondary stage has reached. Whereas in the fourth type, which is very funny, that it has directly gone from the primary stage to a secondary stage, especially when we were testing in the unconfined condition at very high temperatures. So the material was not able to actually respond, behave like what we expected it to show, but it was just it just failed, or it just flowed. So it is very important to understand like what are the conditions at which you have to test it, or whether to understand that one testing condition may not work for all the samples. So there is no point in telling you a standard test parameters in terms of what is the testing loading, what is the testing duration, or what is the confinement condition that we have to apply, right? Now, there has been various studies which has tried to correlate this flow number value with the rut depth in the field in terms of accelerated loading facility studies, okay? And field course. So they have taken field course and from accelerated loading facilities and correlated with the flow number value, because flow number is something which you do in the laboratory, right? Sorry about that. Okay, so this is something which has been developed for normal HMA mixes. Now you can see that it is possible to develop such relationships, but which connect the flow number, which connect the field rut depth and the traffic level. Now we don't have any such relations available for RAP, something which you can think about, or which you can start exploring. Now I'll quickly show some results from the literature from this flow number test. This is one study. I have put the name of the paper also here. This is on the rutting resistance of asphalt concrete mixtures that contain RAP. So they have studied on various surface mixtures, various binder mixtures, and some SMA mixtures also, stone mastic asphalt also, but which we have not presented here. As you can see here that what we expected is that from the previous lectures, what we understood that if you add RAP, it will actually increase the stiffness of the material. So we can see that your rutting resistance will be more, or your flow number is actually going to be more, because it will take more cycles to fail, right? But what is seen here is that this is for the surface mixtures. We see that as the RAP percentage varies from 0, 10, 12, 15, 20, and 25, you see that the flow number is actually flow number is actually increasing, which means flow number is actually decreasing. So this is y-axis, this is a flow number in cycles. You see that it is decreasing for the 25% RAP condition. So it was surprising to note that. So essentially, they have tried different binders, and you say that you add the fresh binder, right? So, and Nivita yesterday explained that you are going for a binder of a lesser viscosity, so that various reasons. One reason is that you need to improve the workability of the mixes. So certain combination of an asphalt binder grade and the RAP mixture may be susceptible to rutting, right? So especially if you are going for a softer binder. So this is something which is worth investigating. And they have conducted some statistical analysis to see what is that factor which is more influencing this flow number value. And they've used some stepwise statistical analysis, and it is shown that the flow number is related to RAP percentage square. So essentially, the RAP content, as it increases, your flow number, the influence of that amount of RAP is actually a large influence on the flow number or the rutting resistance. So it is very essential that we need to explore on this further. Now, this is another study. Again, this is on a dynamic modelers and repeated load test of cold in place recycling mixtures using formed asphalt. Now, excuse me for the moment for this term formed asphalt and all, because I'm sure that these contents like formed asphalt and all will be discussed in this FDP at a later stage. So for the time being, just understand that it is a RAP mixture, and they have tried with different RAP contents from different sources and use this formed asphalt as the fresh binder, and saw that they've tried to rank it. I'm sure this is not clear to you, but forget about this, what is written here, because it indicates the different sources. Okay, so they have used different sources and tried to find the flow number for these materials in the laboratory, and it is seen that as a RAP, as the formed asphalt content varies, the relative ranking of the material has not changed. Okay, whichever was better in the second binder content also. So flow number is consistent in evaluating the rutting potential of wrap materials is something that they have concluded from that. Again, this is something which we need to explore. Okay. This is yet another study. Okay, wherein they have gone up to 45% of wrap. Okay, they call it as a high wrap mix. With super pave mixes with wrap and with HMA and the high wrap with warm mix asphalt also, because you can see here there are studies about high wrap with warm mix in Florida state. Again, this warm mix technology is something that will be discussed by Dr. Asif in the coming lecture. So you can leave that part of what is this warm mix, but just understand that this is a HMA wrap mix. What they have done is that they have tried to see whether there is a flow number to 2% strain of the test is possible or not. Why? Because see, essentially, if you run a flow number test based on the condition at which, if it's a stiff mix, this may go for a large number of repetitions or load cycles, when you can see a 3-stage, right? So even if you do it at a high temperature, this may take like days and hours to conduct one test. It may go up to even 6 hours for to reach the 10,000 cycles, load cycles, or to reach 5% of strain. So they wanted to see whether you will test it only up to 2% of strain and see whether it is related to flow number. So they have found out that there is certain correlation between this 2% strain and the flow number value, and they have established a relationship. But when in this particular study, when they used this high wrap, they tried to fit the same thing in this relationship, and they say that it doesn't fall in that region. Okay, which means that using a 2% strain and trying to fit it with flow number is not going to work if your wrap percentage is different. Okay, so there is the scope of research wherein you need to establish a proper flow number testing protocol with high wrap mixtures, especially if you are going to use other additives like a warm mix technology or a foam bitumen technology is being used. Now, each one of this will respond differently. That is what I want to highlight here. Okay, so moving on. What we have discussed so far is a flow number test and a flow time test, right? Now, the third one is that you want to suppose, essentially, we just want to rank different binders, right? You have rank different mixtures, okay? You have like certain different percentages of wrap. Your whole idea is to see which one performs better. That's all. You don't want to see how over a period of time it responds or not. So in such a case, you do something called a torture test, okay? So this is a simulative test wherein you apply the load exactly as what you see in the field, like a to and fro kind of a motion on a bituminous mix surface, and then see how it deforms. So you see here, this is a Hamburg wheel tracker, wherein this is the specimen which is filled here, and this is a dry wheel tracker, wherein at the bottom here you can keep the specimen, and this is a wheel which will be here. You can fold it, and the wheel comes on top of the specimen, and the wheel will be allowed to move to and fro. You will actually measure what is the deformations. I'm sure everyone is aware, everyone knows about it. There are different asphalt analyzers or asphalt testers or wheel trackers available across the world. So normally we use the Hamburg or the a dry wheel tracker. Essentially, the difference between the dry and a wet one is that here you can fill it with water, and then you can test the specimen under moisture conditions or submerged conditions. Okay, in the dry wheel tracker, it will be on the dry specimen. Now, this is as per the European standards. We have AASHTO standards as well. So this is typically done as per the European standards. You can have different size of devices like extra large, large, small, and so on. And then based on the size of the sample, the loading pattern also differs. So I don't think I need to go into details of this. So like it is typically a B load having certain, say if you see at the small scale loading, there's a 700 Newton being applied, and there will be a loading frequency of 26.5 cycles per minute, or it's like 53 passes per minute. It's like a to and fro pass. Okay. So this is the loading arrangement. You see the specimen here, and this is a wheel, this is a loading, and this is essentially an environmental chamber. You do it at high temperatures because you're looking at rutting. You can keep the specimen in the chamber for sufficiently long time so that the entire specimen becomes, comes to that temperature. Normally you do it at 50 or 60 degrees Celsius, and that is about the conditioning. And you can measure the deformations using LVDTs at various points. When the wheel passes, at various points you can measure what is the deformation, right? And this test normally will be conducted at least for 10,000 cycles, or you can till a rut depth of 20 mm. The average depth of deformation, you call it as a rut depth. Okay. Now, how do you post-process data? You can simply draw the rut depth versus the number of passes and see how the rut varies. I'm sorry, I have not put a graph here. Or you can compute certain indices based on this information. One is called the proportional rut depth. It is kind of a strain kind of thing. Okay, you see what is the initial rut depth at one point, and then what is the current depth at a particular load iteration, and difference will give you the depth, and divided by the thickness of the specimen. Normally it's a 50 mm thickness, so thickness of the specimen will give you a strain kind of a value. Now you measure it at like some 25 or 24 different points. You average it out so that you will get the proportional rut depth at one load cycle, so that you can find it at every load cycle. You can find what is the proportional rut depth. And the another one is that you find out what is a wheel tracking slope. You take this wheel rut depth at two different points and find what is the slope in between. So here again, you can see that in the wheel tracking test also, this material essentially follow a primary secondary kind of a thing, though you may not see it explicitly, but you can see that there is some kind of a increased deformation. So it is a primary stage, and then a secondary stage will come. So that's secondary is somewhere, it is expected that from 5,000 to 10,000 cycle, you will be in the secondary stage, and you try to find the slope of that stage. Okay. And there are other post-processing, like you will find out what is the number of passes required for 20 mm rut depth, or what is the rut depth at one particular number of pass, or you find out how many number of load passes for 1 mm rut depth, or like what is that is called the dynamic stability, or so various protocols or various researchers have tried to estimate rut depth or establish some relation with the number of passes and the rut depth. Okay, essentially based on like how many number of passes you were able to conduct this test, or what is the test temperature at which you are looking at, so you can post process the data. Now what is important is that there could be a lot of variability associated with it. Okay, so one has to be, so this essentially shows the green band essentially shows from this study, they show that there could be variability in the number of passes corresponding to a predefined rut depth. Also there could be variability associated with the number of rut depths at a predefined number of passes also. So if you conduct tests for multiple specimens, there is a large of variabilities that you can expect in such kind of a test. So it is necessary that you need to be very cautious when you use this information for any further processing. But this can essentially give you an indication of whether there is some premature failure susceptibility of this mixtures. Okay. Especially in the case of wrap, if there is some sort of irregularity in the performance, something can be noted. So in that way, this could be helpful. Okay, or a ranking procedure. Basically, if you have like 10 different mixes, you just want to know like which one will perform better, and in terms of rutting, you can go in for a wheel tracker kind of a test. So some results from the literature again here, you see that this is a dry rut test results that are provided for wrap mixtures. This is for the wet test, and this is for the flow number test for the same study, from the same study. This I've taken from Roja et al. 2020. We see that they tried different mixes of like 0% wrap, that is not normal HMA, then 15, 25 and 35% wrap, and see that the 0% wrap has rutted. This is average rut depth in the downward direction. So the rut depth has increased drastically. Whereas in the case of 35% wrap, the performance was much better in terms of rutting. Whereas when you do a wet test, this variation in response is not seen much. You see that, the difference between wrap mixture and the normal mixture is somewhat visible, whereas but whether 25 is better or 35 is better is not something that can be made out from this wet test. Okay, and this again is a flow number test which we have discussed. Okay, now so to sum up of what we have discussed, in the rutting characterization, you can go in for a flow time, flow number, or a wheel tracker test, which can give you substantial information. But it is very important that how you know, how you frame the or how you design your experiment, the loading, the conditioning, the confinement conditions, and everything. So that is very important. Okay. Now coming to the fatigue characterization. So what we have discussed is about rutting that happens at high temperatures. Now fatigue is something, or fatigue failure is something that happens at the intermediate temperatures or with low frequencies. Okay, when the material is mostly brittle, then there is chances of it closely behaving like an elastic solid and fracture starting. So when if you look at the loading, the number of load repetitions that happening on the I'm sorry, okay. So the number of load repetitions that is happening, there will be an initial stage when the stress distribution could be uniform in the material, and then there will be certain stage will be reached when there is strain hardening happens. Then there will be stress concentrations will be happening, and then there will be the formation of these micro cracks being converted to macro cracks. So it is cracking is not something again which doesn't happen over the instantaneously. It happens over a period of time. Where these micro cracks, there is a coalescence of the micro cracks, and gradually it will lead to a macro cracking. Okay. Now, when you want to study about the fatigue response of a material, you can go in for a laboratory test, like what we have done for the fatigue, like for the rutting. You do a repeated stress test and see how the strain response, or a repeated stress strain analysis can be done till the material leads to a failure. That is one. So this failure kind of a fracture kind of a test, or you can see how the material, see, as we see that there is accumulation of energy, there is dissipation of energy with load cycles. So you can have an energy dissipation study, or you can use approaches of fracture mechanics to study how this the fracture actually initiates and how it propagates. So a fracture mechanics study can also be done as far as the fatigue life of a bituminous mixture is concerned. Now, the various factors in the pavement structure, what are the various factors that leads to the fatigue failure? You have the load, you have the volumetrics of the properties of the material, the pavement temperature, the moisture condition, aging of the bituminous mixture. When I say aging, the properties of the wrap inside it. And then there is something called the rest period and healing. I think somebody has mentioned in the last lecture. See, if you allow the material, yeah, I think Sudhagar Reddy sir has mentioned this. So if you allow the material to rest for some time without loading, is there some sort of a healing that happens in the material? So essentially, you want to study the fatigue characteristics in the laboratory. Now, how is it reflected in the design? In the design, as per IRC 37, it tells you that 20% cracking is considered as failure, and the critical tensile strain at the bottom of the bottom bituminous layer. Bottom bituminous layer is important, which goes into this distress transfer function, wherein you can find the number of repetitions to failure. So what is important is the tensile strain at the bottom of the bituminous layer. Okay. Now, what are the different modes in which you can find this tensile stress strain behavior of the material? You can have a tension compression test on a cylindrical specimen. You can have a 2-point bending. You can have a 3-point bending. You can have a 4-point bending, or an indirect tensile strength. So what we will be discussing is this 4-point bending, which is very popular and familiar. Okay. So the current standard, it's ASHTO T32117. We had ASTM standards and the European standards. So just a glimpse of the comparison of the various standards is given here. So essentially, we will look into this ASHTO T321, wherein you apply a Haversine or a sinusoidal loading at different strain levels you can do. This is essentially done as a strain control test. Why? Because you are holding a beam specimen and you are trying to apply a loading unloading kind of test. So in that case, it will be better to control the strain within a certain limit, and then you see what is the stress response. Whereas in the case of a permanent deformation or a rutting testing, it will be better you load it and see how the deformation happens. So the load, controlling the load will be better in that case, but here it is better to go for a strain control test. Okay, so you'll give some initial 50 cycles for the seeping essentially, and then you do a number of repetitions of the loading cycle, and then again the experiment will be stopped when you see what is the stiffness, or you compute something called the stiffness of the material, and based on the stiffness you multiply the stiffness with the number of cycles. You see that it goes like this, and when it reaches a maximum value, and let it come down by at least 15%. So when you get a graph like this, I'll tell in a moment what is stiffness. Okay, so if you get something like this, you are expected to test the specimen at least till this stage. Okay, a stage something like this, you need to see a peak point and then it goes down. So till such time you are supposed to test it, right? So this again will differ from specimen to specimen, and accordingly you can choose that. So this is the specimen preparation. I've taken this from Dr. Padmarekha. You have the sieving, the batching, then the mixing. You compact the specimen in a press box, and then you get an original beam which can be sliced according to the required specimen. And these are your sliced specimens. So this is a 4-point bending arrangement. You have the 2 supports and the 2 loading points. That is how the 4-point arrangement is there. You see the arrangement here. And then there are 2 ways in which you can test it. The first one, as per ASTRO, is that you apply a sinusoidal load. That is, this is original beam. You go up and go down from the neutral axis, right? So this is this is bending in both directions. Whereas you can have a Haversine also, wherein you will have the beam. You will go down, then you come back to the original position. You don't go up. So essentially, it is like no deformation in one direction, or it's only Haversine. It is not the complete sinusoidal. Okay. Now these are the loading points. It is P by 2, P by 2, A are the spacing between the 3 points, or the 3 spacings, and essentially L is the distance between the 2 supports. And you have the loading. If you apply the loading, the displacements will be like this, or you will control the displacement as one particular strain, and you will note down how the stresses are varying. So you can see here, this points represents the strain. It is not the same value because it's very difficult to get a uniform exact same value always. So essentially here, this is the maximum tensile strain. Say it is kept as 400 micro strain, and you see that the tensile stress, the maximum tensile stress of that pulse is noted here, and you see that as the strain increases, you can see that the stress decreases. Okay. Now the test temperature has to be decided based on the effective test temperature, which is related to the mean average pavement temperature like this. Now, this is the 4-point beam bending. You have the moment equation. Why a 4-point beam bending is that? Because in between the 2-point loads, you will get only bending and no shear. So that is why if you go for a 4-point beam bending, this is your classic bending equation, from which the flexural stiffness is denoted as sigma T by epsilon T, and the phase angle between a stress cycle and a strain cycle is given by 360 Fs, where S is the time lag between this is small s actually, okay? S is the time lag between the peak stress and the peak strain. Okay. Now this is the typical stiffness curve. That is the stiffness that you have measured. It is denoted as E here. You can assume it as capital S. Okay. It starts with 0. There is a phase 1. At the end of the phase 1, you can say that there will be the starting of the micro cracks, and then that goes to this phase 2, and then comes to phase 3 when this macro crack starts, or you say that the failure is starting. Okay. Now, this is the stiffness modulus, which has been plotted for various cycles at different strain levels. You see that this is plotted for different strain. We are testing at different strain levels of 200 to 800 microstrain. You will get data like this. So this is a typical data that you get from that. And again, you can have different post-processing techniques. You normally go for a normalized modulus. You see the phase angle, or you can have the energy dissipation techniques. Okay. This is what is called a normalized modulus. At every point, you can find what is the modulus with respect to the original modulus. As I said, original modulus is after like the 50th cycle or so. The 50th cycle or so will be taken as the first point. So into the number of number of cycles of that ith point by the number of the original, the first point. So this will typically follow a path like this. It will reach a peak point, and this peak point will give you the fatigue life of the pavement. of the mixture, right? So you can either look like this, or again, as in the case of rutting, you can like fit a polynomial or a logit model to this to see what is this peak point. Now, do we get the same shape always? Not necessary. You can see that these are different responses. This is the stiffness modulus is given in black. That's a decreasing one, and the increasing one is the normalized modulus. Okay, you see that it could keep on increasing, and within the test duration it may not come down, or it may come down. Excuse me for this change in the color, because in the literature it was like that. This essentially is the normalized modulus. Okay, so it is increases and decreases. This is a typical response, or it keep on increasing and somewhat comes a steady state, or it keep on increasing like this after reaching a point like this. So there could be different responses, and one needs to be very cautious in interpreting these data. The second one is, ma'am, I hope I can take 5 more minutes. Tushara ma'am, is it okay if I take
yes,
5 to 7?
Sure.
I'll quickly finish. So the next approach is that you use a Lissajous plot. Now, what is Lissajous plot? It is a plot drawn with the stress versus strain, right? So this is your normalized modulus. If you consider like one point A, B, C, and D, if you plot the Lissajous plots, you see that at A, there is a typical ellipse. Whereas at B, it started slightly changing. Whereas at C and D, you see that there is no particular elliptical shape. It is all disturbed, right? Kind of thing. So we see that the failure has happened when it reaches C and D. So this Lissajous plots could give you some indication of whether the material is still in its, it is fatigue life, or it has reached its beyond its fatigue life. This is a similar picture. Now, the third approach is using the energy ratios. You can compute energy from this, again from the stress strain curve. You'd see that energy is calculated as pi sigma 0 epsilon 0 sine delta 0, where sigma epsilon are the stress and strain, and the delta corresponds to the phase angle. Now we can see the original energy by the energy at the end cycle into N will give you the energy ratio. And this energy ratio can be plotted, or N W0 by Wn give you the energy ratio, as you see here. Sorry, it is denoted. Okay. So you can plot an energy ratio. This is doesn't happen, there is not a sharp change happen. So you can just plot two tangents here and find where there is the this changing point, and that point will correspond to the fatigue life. This is one way. And another way is to find the ratio of the dissipated energy change, RDEC, wherein you will find how the energy varies, like Wm minus Wn by Wm into N minus M. Essentially, it gives you the rate of change of this dissipation energy. So you can see a secondary plateau here, and this essentially gives you another indication of where it starts failing. And this is the phase angle thing. You can note the phase angle for all the cycles and see when the phase angle starts dropping. That is the stage corresponds to the failure life. Now, this is one literature which studies about the RAP mixtures. So the first fatigue life. So you can see that this was a normal mixture. They've used like some 35% RAP. The fatigue life has come down. Okay, so your material is actually become stiffer in this case. When they use two rejuvenators, again you will be discussing rejuvenators at a later stage. So you see that as you add the rejuvenators, the fatigue life could be improved. Okay, you'll have further discussions on this later. Now, moving on, the last test which I will be discussing in this session is the semicircular bending test. So what you have studied, this is like a fracture mechanism kind of thing. You are actually, fatigue life is being explored in that previous test. But what here we are trying to do is that you are trying to fracture this material. So it is kind of an indirect tensile test. So what you do is that you cast a semicircular specimen and load it from the top. So this is your specimen, and you put a notch here to see that the failure happens only through that point. Okay, so essentially you can cast a larger specimen and slice it into thin specimens like this of 57 mm height and 150 mm diameter, and this notch depth that is suggested, and the code is ASTM D804416, and the code suggests that you can have notch heights of 25, 32, 38 mm and so on. This notch height has an influence on the fatigue or the fracture behavior. And what is done is, and again you can have a PG intermediate intermediate temperature, normally 20 to 25 degrees Celsius is at which you will test a specimen. You can test it in a Marshall specimen, Marshall apparatus, or you can test it in your AMPT also. So when you test it, it is important that the loading has to be applied at a controlled rate of 0.5 mm per minute, and you can terminate the test when the applied load decreases to 25% of the peak load. That is when the cracking has already started. You can stop it, and then you draw something called, you compute, okay, this is a load displacement graph that you plot. You see something like this. The load keeps on increasing. When the fracture has actually started, it will go down, right? From this, you compute what is the strain energy till failure. So what you do is that till failure, that is till this peak point, on the left hand side of the peak point, you can find what is the area under the curve. So you can just use a quadrilateral equation, or you call it as a trapezoidal equation, to see, like, cut it into small trapezoids and add them together. So this essentially will give you the total strain energy till failure. Or you can again fit a polynomial and find what is the area under the curve. And then essentially you find what is called the critical strain energy release rate, JC. So what you do is that you calculate the strain energy, and then for different notch depths. So as I said, there are 3 notch depths. So you find the strain energy at 3 notch depths. You find and these are replicate samples. You fit a straight line with that and find the slope of that. So that will essentially give you du by dA divided by d, which is the sample thickness, will give you this critical strain energy release rate. Okay, this also gives an indication of how this energy is being released, or how quick this your material is going to fracture or not. Okay. Now, there is another way of post-processing this, is that, again, this is the load displacement curve. You calculate the area under the full curve. Earlier, we have considered only half of it, or not half, sorry, it is till the failure. Here, you have till the maximum point. Now, you are considering the full curve of the test. Then, you compute what is called the work of fracture. And then the ligament area is given as R minus A, where R is the sample radius and A is the notch height. Okay. So then the remaining that into the thickness will give you the ligament area, and you compute the fracture energy as WF by A, and you compute something called the flexibility index. So GF by absolute of a slope at this point. Okay, so this is way in which it is starting decreasing. So at this point, you can find what is the at this straight line point, you find what is the slope, absolute value of that slope. When you divide it with this fracture energy, it will give you one index called the flexibility index. I'm sure I can quickly go through this. So essentially, this is one semicircular bending test result that has reported by Roja. You see that there are like different wrap percentages, 0, 15, 25, 35, and so on. So what is seen is that as the wrap percentages increase, you see that this area of this load displacement curve has reduced. Okay, so the mixture with higher wrap content has reached this peak load in a less displacement length. Now, this is another way where this fracture index is, the flexibility index is plotted with respect to the wrap percentage. You see that a lower flexibility index is that indicates, see, this is 35% wrap, which shows that there is a lower flexibility index, which essentially shows that there is a higher brittleness of the material, which has lead to the failure of the material at a faster. So from the study, this examples that we have shown is that we see that when your wrap is being added from like up to 35%, your material has actually become brittle. Okay, so the fracture failure has happened at a faster rate. Okay, so to summarize, in rutting, what we have seen is that when you use wrap mixtures, especially the cold recycling mixtures, it is porous in nature, right? And if you are using, and this porous material will have a larger influence when you do it under a confined condition or an unconfined condition. If you confine this material, this porous material will get chances of deformation, which will be more. So if you want to actually mimic that, if you actually want to capture that response, it is necessary that you do it in the confined condition, whether it is a flow time test or a flow number test. That is as far as the cold recycling mixes are concerned. Now, if you consider the hot recycling materials, this may give different creep responses, and it is necessary that you fix the loading time and the respirate time. Right? So what we have seen is that you will give like 0.1 second loading and 0.9 second rest period, indicating some amount of the traffic speed, but it need not give you the correct creep response if you have a hot mix recycled material, wrap material. Okay. Then see, what I've shown you is that this field, this laboratory data that you collect as in terms of flow number. Now, how does it correlate to the depth in the field is something that has to be investigated. So it is necessary that you keep on collecting information from whether it is a field test, whether it is a actual payment, or whether it is a test track, or whether it is an accelerated loading facility. It is necessary that you keep on collecting information that can be correlated to this flow number value. Okay. Now, as far as the fatigue is concerned, the fatigue response, the wrap material might show different energy dissipation. See, I've shown you like how the energy dissipation is computed. So this damage of a wrap mixture may be very different as compared to the typical mixture. So you need to quantify the same. Now, this energy ratio, normalized modulus, are all based on HMA. You need to see whether it works for wrap mixtures as well. So a lot of data collection in this direction is needed. And a fracture test like SCB are loading sensitive. As I said, it have to be applied at a particular loading. Then the influence of loading rate on wrap mixtures is to be again investigated, because that loading rate for HMA has been has been devised based on a lot of experimental studies and field data. So to conclude, it is necessary that you identify what is the optimum wrap percentage for a wrap performance. Also, you find what is the optimum wrap performance for a fracture or a fatigue kind of performance, and then you need to get a balanced design, because you want your mixer to perform both ways. So you need to find a balance and get which is your optimum mix. So with that, let me conclude. Thank you, Ashalata ma'am, and thank you to Shara ma'am for this opportunity once again. So let me stop my sharing. I'm sorry I exceeded a little bit the time by a little bit. Sorry. Okay, shall I stop sharing?
Now the floor is open for queries. Participants are requested to unmute and raise your queries, or they can post the questions in the chat box. Due to time constraints, the queries can be addressed during the detailed discussion session. So
I think one query is already in the chat box. We can address that.
Sorry, I can't see that question here.
Yeah, it is by Ujjwal Solanki. Please guide what is the criteria for flow number to accept the mix.
Sorry, what is the criteria for?
What is the criteria for flow number to accept the mix?
To accept the mix.
Yes.
Oh, okay. See, there are NCHRP report gives you some recommendations on what is the recommended flow number, but that is only for bituminous mixes, and that too is not followed precisely. Essentially, again, now we use this flow number test basically for a comparative study, or basically for a ranking kind of purpose. There is not solid relationships as on like what should be the flow number when you can say it is acceptable or not. So there are certain I think I don't have it here, but there is some like number. This is related, the number of FN is related to the performance, and the acceptance criteria is there. I can get back to you on that by 9:30. Okay, 9 o'clock session.
Hello, Nidhi Chichi, Kavita here.
Kavita.
Hi, Chichi, very nice presentation. First of all, I should say, I have a doubt regarding that flow number graph which we are showing regarding the RAP percentage. No, so in that graph, for higher RAP percentage, the flow number is decreasing kind of. And even in the every particular RAP content, we cannot generalize like how these flow numbers are varying. So, how could we get a trend for that, or what is the means for generalizing it?
See, that's what. That's the whole point. See, the test procedure tells you that you have to apply this load over a period of time and keeps on calculating, measuring the epsilon p, right? The permanent deformation. But in certain, see, the study, I think I've stopped presentation. The study by Roja has shown that they have an increased performance when they went from 0% to 35%. The flow number has actually increased. Like when I say increased, its rutting performance is better, right? Whereas certain other studies have shown that it is not like that. It is the performance has actually decreased. So this is something we need to investigate and see, there could be various reasons also. There could be one reason that the way in which you are capturing that flow number, as I said, see, when we were trying to post-process it, it was taking some random local minimum as the flow number. That is why we went and looked at the various post-processing algorithms. So that could be one reason, but I suspect that is not the reason. The material, it was interesting to note that in that study, whether it is for the surface mixes, whether it is for the base mixes, and even for SMAs, they got the similar trend, which means that what they have mentioned there is they have added like a softer binder in order to improve the workability, or what Nivita mentioned, etc. So that could be a possible reason that the performance or the rutting performance has come down, okay, as the RAP percentage has increased. So this is something which we need to be very careful. You can't just look at one flow number value and decide on make a decisions based on that. I hope I answered your question.
Yeah. Thank you, Shishi. Again, regarding this rest period and healing time that we are considering. So, can we go for the same thing for RAP also?
Not necessary. We can't because see, what is the idea behind 0.1, 0.9 was that it relates to certain speed that 12a by s. You find that based on that you find out that okay, this represents when a wheel passes, this is how the response will get transferred to the material. So in 0.1 seconds that wheel will load the material, and then 0.9 seconds in 0.9 seconds the next one will come. But in the case of RAP, based on the stiffness of the material, or the way in which is the interrelation of the materials, this loading, the 0.1 loading may not completely load it, and the 0.9 seconds may not give you enough rest period. Okay, even that is important even in the case of bituminous mixtures. We have tried for longer rest periods as well, rather than giving a 0.9 seconds rest period, we have tried to give elongated rest periods to see how the material responds. So again, they've come out with various studies. It's averaged out, right? So there has been conducted many studies, and it's an averaged out, and in order to make the protocol is developed such that it can be applicable to many mixes, but it may not be applicable to everything. See, that again is something which we need to see, like how the rest period affects the performance. Again, healing is another aspect, because I've not mentioned any references which have studied about the healing of RAP mixes. But Sudhakar Reddy sir actually mentioned it in his presentation. So healing is another aspect which need to be explored.
Thank you very much, Chechi.
Thank you.
I would like to invite Mr. M. Surendranath, Research Scholar at NIT Calicut, to thank Dr. Neethu Roy.
Yes. Thank you. I would like to thank Dr. Neethu Roy, Professor from Mar Basilios College of Engineering and Technology, Trivandrum, for accepting the request and delivering a presentation on fatigue and rutting characterization of bituminous mixtures with RAP. Ma'am, really, it was a very interesting session. You talked about the laboratory-based testing methods for determination of rutting potential and fatigue life of HMA mixtures. You have elaboratedly explained about the test procedure and the test conditions that are to be followed as per the code. And also you have combined the RAP material with by taking some of the literature studies, some of the results of the studies, and you have also specified or highlighted some of the points wherein the research can think of, like for example, the correlation of flow number versus rut depth of RAP material. And you have talked about various tests like flow number, flow time, wheel tracker, 4-point flexural beam, and semicircular bending test. You have talked about various codes and various specifications that are to be followed. And I once again thank you very much for this wonderful session, madam. We'd like to have many more sessions like this in the coming future. Thank you very much, ma'am.
Thank you, Surendranath, for that very detailed summary. Thank you very much. It's okay.
Participants are requested to keep posting the queries, which will be addressed during the discussion session. And as there are more queries awaiting answers, I humbly request you to join for the detailed interaction session scheduled from 9 to 9:30 p.m. after the photo session. So without further ado, let me welcome our honorable speaker, Dr. Asif Ahmed, Ingevity India Private Limited. He did his PhD from IIT Madras, specialized in pavement material characterization, and his master's in transportation engineering, specializing in pavement. For the past 14 years, he has been involved in research and development of asphalt and other pavement materials and is currently the business manager for pavement technologies. His responsibilities include technical formulations and evaluation of applications such as microsurfacing, warm mix, hot mix recycling, and cold mix. He and his team also engage in quality control and assurance of hot, warm, and cold asphalt applications and customer support in India. Let me welcome with great honor Dr. Asif Ahmed to deliver his talk on hot mix recycling. Before going on to the talk, I request all the participants to turn on their videos to take photographs. Participants are requested to turn their camera on.
Serena, can you see the this frame of all the participants? I'm not able to find.
Yes, ma'am.
I can see only your screen.
Again, we select the grid, view grid. On the top right corner, view will be there. You can see the grid.
Ah, okay. Nice to see all the participants together. So I have taken the photograph. I'll share with you the photograph. We'll go for the second session.
I welcome Dr. Asif Ahmed to deliver his talk on hot mix recycling.
Thank you. Good evening, one and all. I think it's a little late, but I hope it should be fine for all of us. Can you all see my screen? I mean, I just to know at least from the coordinator that.
It is not in full screen.
How is it now? Is it okay?
Now it's fine.
Yeah. Shall I proceed?
Sure, please go ahead.
Yeah, thank you. Yeah, good evening, one and all. And I'll just start with a small introduction of the company where we come from. So Ingevity is one of the largest producer of asphalt emulsifiers and additives. We are also into various other verticals like automotive carbons, dispersants, agrochemicals, kappa, and oil field chemicals. So asphalt is one of our most important, emulsifier is one of the most important products that we do. And we have been pioneering in that for many decades. To give you a simple snapshot of what we do, we cater to various applications. Typically, you can see from maintenance to new constructions as well as rehabilitation. So in rehabilitation, we cover both the cold recycling and hot recycling, and new road construction, greenfield projects, environmental projects such as warm mix asphalts we do. And for preservation and maintenance, we go solutions such as microsurfacing, cold mixes, and various other treatments such as chip seals and things like that. We do have certain R&D centers for us. Typically, our R&D center is at USA Charleston, but most of the other labs are for development purposes. We do operate from the IITM Research Park laboratory here. Okay, so to come into that, this picture clearly shows how exactly we do that. So if you see, this is a typical, I put it like DBM and the BC layer with a surface treatment on the top. So this picture clearly shows what kind of applications happen at which regions or the zones you see. So typically when we talk about recycling, and of course my focus will be mostly on hot recycling for today. I won't be touching much on cold recycling or other pavement preservation titles. So when we talk about recycling, it is going to be mostly either a full FDR or a partial the reclamation that we will be doing it. So here FDR, we are not talking about hot mix part. So we'll cover simple options such as what is hot recycling and the two types and what kinds of technologies are mostly used for these kinds of purposes. Yes, a snapshot of what are the challenges that we see and the current practices, what we are involved with, especially with hot recycling is concerned. So my focus here mostly will be on the technologies such as warm mix and rejuvenation. So hot recycling, we all know what it is. It's an on-site in-place maintenance rehabilitation method consisting of heating, softening, scarifying, and doing a work on-site without taking anything to the plant or something. The same way, for example, your typical step, first thing is we remove it. We add an recycling agent, sometimes yes, sometimes no. And why we add the recycling agent or what does it do, we'll be seeing it in detail. And I'll also try to show some of the projects that we have done across the world. And we also have, especially we add this hot mix part also. How much of recycling we are going to add is the total impact that we are going to see here. So another simple example, how do we feed the wrap? So either you feed the wrap cold feed or you heat it and preheat it and feed it. In cold feeding, what we do is we don't go beyond 20% because it's difficult to handle it from a plant production perspective. It may be a design perspective is different, but when you go to a plant, if you're going to feed it cold, it is not going to work. The mix is not going to be proper or uniform. So if you want to feed anything more than 20%, then you have to preheat it. So this is a typical arrangement, what they do. So the wrap is taken in a drum and then used a belt to take it to the pug mill, and then there it's mixed with the hot mix part. Hot mix means with the virgin aggregates based on the calculations that you do for the asphalt content, and then produce it. In the other case, we just have a heater just before the feeding part. So in plant recycling, we have a full-fledged plant, a batch mix or a drum mix. Mostly, as I said, direct feeding happens for cold or direct feeding. If you want to do it without heating it, it's only 20%. If you can preheat it, you can go up to 30 to 50. Again, 50 is a number which currently is what hot. I mean, in the sense, 50 is achievable. We are not, nobody has gone beyond 50 in hot mix recycling. In cold mix, you would have gone up to 90 or 100%, but hot recycling has its own limitations but 50% is what maximum we can achieve, with the idea that we'll get all the required properties that we want to achieve. So some of the challenges that we typically see in hot mixes, the first thing is the wrap variability. I mean, this is more related to the zone where we are working. In India, if we look at it, with our experience, we have seen enormous variabilities. I mean, within a single stretch, you get different kinds of aggregates. It may be to various reasons. For example, depends on the history of the road. A road typically has, for example, a road has a lot of patches. The patches, the gradations are completely different. When you do a patch, we use a very, very fine aggregates. The quality is different, the material is different, the binder was different from what they used before. Typically, again, there may be a lot of overlays that have happened here in 30 mm, 40 mm, and things like that. So the wrap variability is a major challenge that we see from our perspective here. Second thing is modification to standard mix design procedures. We don't have a specific kind of a procedure for doing hot mix recycling. We are currently adopting the same one. What is the difference that makes here is, if you look at it, in hot mix, we do a proper design based on your what Marshall methods or whatever the design specification gives you as for IRC 37 and things like that. In hot mix recycling, what happens is I need to understand the wrap first before I do the design. What kind of wrap we are going to get it, and then only I can decide what kind of gradations I should use or what kind of temperatures I should use, etc. So that is one thing. Maybe there is a lot of scope still for the specifications that has to still come up on the recycling part. Control procedures with wrap mixes are a little difficult, again, because there is a lot of variability. This is again directly related to the first point what we said. And another interesting factors what we come up, I mean, these are again all related to the field what we see. Particle clustering. This particle clustering is very interesting. The thing is, people collect a lot of wrap, they keep it at the site, and the project gets delayed, or for some reasons it is not as planned. Like for example, today I collect my wrap, I'm not going to do the work in within 3 days or next 5 days or 10 days. I don't know when the project will start, when the mix design will be ready and things like that. So in the meantime, what happens when you start collecting the wrap and accumulating it and creating an inventory on that, you leave it like that for 2-3 months, it gets attached with each and everything. So it becomes again a bond. So again, the gradation is an issue. So I don't, even if you segregate it based on different gradations and then store it, if you give some time, the wrap gets agglomerated into it. And adding to that, these aggregates typically have the property of absorbing a little bit of moisture. So again, we need to take care of those things. So particle clustering is a typical issue where more wrap work has been happening as of now. This is an area where people like to study, how do we do it, what can we do, how much of time is required. For example, if I want to, I have segregated a wrap. So what is the timeline before which I need to use this? See, there are a lot of those kinds of activities that is currently being faced at site. And typically when people try to crush more so that you need the right size of aggregate, they also end up creating more of a dust, which doesn't help in the whole optimizing the wrap usage. Now, another challenge is when you start using high wrap, the metal is already brittle, it's hard, and then it starts giving premature cracking or fatigue cracking. You can see much earlier than what you see in a hot mix. And since wrap is already used asphalt, it needs higher temperature if you want to use the binder present in it. So if going to the practices, I have just highlighted these two things because considering the fatigue cracking and production temperature issues, how these technologies can be addressed. I mean, these technologies addresses these kinds of issues. So challenges, if you look at it, will address these two. So current practices, there are a lot of developments happening on the factory side or the mechanical side of it. So when people want to, first of all, you need when we started, RAPS was introduced in the hot mix plants. One of the major challenges, where do I put it? Where is the bin for my hot mix? I mean, where is the bin for my RAP in the hot mix? So there are 2-3 bins for three different sizes. Now I have one more new material, which is the fourth material. So I need to first of all modify the plant. Now, if I modify it, I want to heat it. So I need a heating arrangement in my plant. So mechanical modifications are gradually parallelly happening such that we are able to use high RAP into it. As of now, 20%, 10% is very easy. If you go to any batch plant, you can see that you can use it. But going beyond 30, 40 is still today a challenge. And there are a lot of people working on that to address that, even from various companies who make plants and machineries. The second thing is using additives and admixtures. So foaming is also a technology where you can reduce the temperature. Foaming, again, the idea is simple, that I don't want to expose my RAP, which is already heated, which is already aged, and which is already lost all its volatile material. So the few things is, one is either I reduce my temperature of my application, which can be adopted using warm mix technologies. The second thing is, can I give back some of the life to the old RAP, the old bitumen, which doesn't have those flexibility in it. So that is where rejuvenation comes into picture. So if you look at what is warm mix, simple introduction is, your typical hot mix working temperatures range from 135 to 160. So 160 is what the temperature at which you heat your binder, heat your aggregates, and at so temperatures that go into the plant, and you mix it at around the same temperature. By the time it comes out, it drops down, and then you take it out, you load it into the trucks. By the time you go and lay it, it's almost around 120, 110. So in a plant, the working temperature is around 160 to 130. Now, when we talk about warm mix technologies, the temperatures are typically reduced by 30 to 50 degrees. So the idea is not to introduce something. The idea is to make it work at source less temperatures. If you are able to achieve what you want at low temperatures, then you don't have to expose your material to a higher temperature. So how do we do it? So typically, this is an additive which typically added into the bitumen, and there without any much of modifications. And this goes and then adds with the aggregate, and then the mix is produced. This is proven a lot in the various developed countries. Typically in the US and Europe, the warm mix technology has been adopted extensively, I could say, because the reason was there is less environmental implications on that, because lower your temperature, lower is the pollution that happens from the plant. So typically, you know that all the asphalt plants as on today are outside the cities. The only reason we don't want to pollute the cities. That is one thing. So when we talk about hot mix recycling, and when we are going to use RAP and again reheat it, again it is going to create a lot of pollutions, and then this is a method which you gives better performance as well as better environmental impacts. So what we typically do, allows more RAP in direct feeding. It increases from, for example, without any additive, still 10 to 15% is typically used. Again, when you want to go beyond 20, 30, and 40, that is where you need all these agents. And second thing is, see, I would put it this way. See, the most vulnerable period any bitumen goes through is before construction. What I mean to say is, a bitumen is heated to 160 degree only once in its lifetime, or I would say before it is started constructed. Once the road is constructed, the bitumen is never going to touch beyond 60, 70 or anything. So it has already got, maybe from the refinery till the plant it comes, it would have been got heated up, reheated up, and then while producing the mix, it's heated at 160. So that is why we do the short-term aging and long-term aging. The short-term aging is typically which tells about your plant till the laying. So from the plant towards the laying is short-term aging. So this is the most vulnerable part. So your metal has already gone through that. And then it has already gone through a long-term aging, which is like 5, 10 years, 15 years or 20 years of the life. Now, after 20 years, you remove the RAP, and then again, we are subjecting it to a higher temperatures. So that is where all the things keep changing. So it already has lost all its volatile material. And now when we want to reheat it, it is not the old temperatures that we are going to choose, that same 160, 150, it is not going to behave the same way. So I need to increase my temperatures much, much way ahead if I want the same kind of response from these kind of material. But that's not possible. I mean, going beyond anything beyond 180, 190, it's just ruled out because there are a lot of other implications on that. So that is where, if you can get those properties within these temperatures, that is well and good. So what typically, if you ask me this product, or what we do is, you increase the workability of any material. If I can increase the workability and I get a good compaction at a lower temperature, then go for it. So typically you reduce the oxidation. When you reduce your temperatures, you are reducing the oxidation of your binder. Your wrap binder is already oxidized. When it is still 10 or 20%, it's okay. Out of the whole system, it is only 10-20%. Now, when you're talking about 30-40% wrap, high wrap, then it is considerable amount which has already been oxidized. So chances of cracking, fatigue cracking, and other brittleness, or any distresses that can happen due to this can be very, very significant when you use high wrap. And rejuvenators, what they typically do is, they are relatively new in the industry. If you look at it, rejuvenators, I see hardly 10-15 years, 15 years, or maybe 20 years. But as of now, for our things, we have seen hardly few projects in India, not on a bigger scale. There are one or couple of few projects that has been done. But rejuvenator, what is going to be the next, what we see, one of the latest technologies that is going to be adopted. Reasons are many. Again, no new aggregates we are going to get. And if you look at it, again, they may be a little different from what we are talking today. Even the aggregate sources are behaving very differently as on today. From the same quarry, you take it from the top of the ground, the aggregates behave differently. Once you start taking the aggregate keep on taking it from the quarry and you go deep inside it, these aggregates behave completely different. So there is a dearth of aggregates and we need to go for higher wrap designs. There is no alternate for that. Maybe if not today, maybe another 3-4 years, we will be sitting on a high quantity of wrap everywhere from every project. So typically, even other than warm mix, we may be needing something to make those binder in the wrap a little younger or whatever we want to do. So there are various recycling agents. Most of it, I mean, these products are now coming into picture. First of all, they are all mostly field tested and more than field tested, they are laboratory tested. There is a lot of data that needs to be supported to make it or to implement. I mean, we need to use it on the field. And if you look at some of the projects what we did on other places, they have gone up to 40% wrap with these kinds of rejuvenators. There are some guidelines as the National Road Research Alliance has given it. You can also refer the Asphalt Recycling and Reclaiming Association manual. That is one of the best to go for this kind of idea, how to use it and what can be the precautions that needs to be taken. So I will, before going into this, I'll just give you, okay, I'm just using the name here. So Evotherm is a warm mix and Evoflux is a rejuvenator. The recent one, what currently in US they are adopting is, for high wrap, a little bit of warm mix and little bit of rejuvenator. I mean, this is like a little hot topic for them as on today. So what they want to do this? So the one is, the warm mix idea is to improve the workability and reduce the temperature. So warm mix doesn't do anything to the binder in the wrap. It only gives a good workability so the wrap gels well and I could get a good compaction at low temperature. Now, rejuvenator like Evoflux, what they do is, they typically given the material that is required for the asphalt to behave such that they are 5 years younger or 10 years younger. So they want both of these to be in one thing. So this is one thing that is happening as of now recently. And another interesting thing, we use wrap, they also use our shingles. The shingles are, I think it's a kind of asphalt mixers that is used for roofing and things like that. They are still much harder and brittle. So when we want to add such materials and lay roads, you need some kind of a combination which works and gives you both. So it gives you better workabilities and better coatings, and we order a little bit of lubrication on the mixes also. So yeah, typical representation, you can just say 0 to 15% of wrap you can in a hot mix recycling, you can use without anything, provided the wrap is not too extremely stiff or very bad, like 30 years old or something, which doesn't have a zero, I mean, which doesn't has a big pen and things like that. Then 15 to 30, a warm mix will be able to help you out. Beyond 30, and if you want to achieve almost 50%, we may need definitely anything above 40 or 50, you need a rejuvenator. Any system you use. So I hope I'll get into some of the projects that we did. I mean, it is just a glimpse of that, not much details of that, how much of what has been done, some related to studies and things like that. So typical studies are mostly with PG grades that we did. And like you have a wrap, you have a controlled material, and then you use warm mix with wrap, HMA with wrap, then warm mix with that, more wrap. So how do you see that, what kind of results they give? So then you extract the binder, do a test on those binders and see what kind of properties. So one of the Missouri's devotee study, one of PG grade showed that. So yeah, warm mix asphalt with 35% wrap could give a penetration on the binder. The residual binder can give you a penetration of 28, which was similar to what an HMA with wrap at 20% could give you. So here, if you see, I mean, just it's again a case that was studied. Like here, you see case 2 and 4, where it is with warm mix was done at 130, and again extracted binder from a hot mix which was done at 160. The properties are more or less similar. So it's like you can, with warm mix, they're able to use more of a wrap. So the wrap in the hot mix was almost around 25%, whereas with the warm mix was around 40%. And still the properties, the ductility, the softening points are more or less similar here and there. So this is a project that was done in China. So here it was like, it was just a less amount of wrap, like 25% of wrap with an additive. The virgin aggregate was heated to 190. The temperatures they used, production temperatures were low. Cold weather conditions. So typically they heat the aggregate to a higher temperature, which is typically in India we heat around 170. So the ambient temperature, you can say it was around 7 degree. The compaction with VMA additives, we could get up to 98 to 100%. So this was a typical batch plant kind of where we heated the wrap feed system was used. And another study related to the Chinese binder specifications. They did the short-term aging studies on the binder. Here it was a rejuvenator. So you can see the graph here with the actual pen of the wrap. I mean, the binder was, I mean, it was nothing. It was almost around 0, a little bit more than that. Then once you start adding the rejuvenator at different dosages, how much of the softening, it's not exactly the softening we reported, because softening is not the only thing you wanted. By softening a binder, you get a good viscosity and a penetration, but you need to also match the ductility and things like that. So this is where we differ. Somebody, I think people may have a question, what is the dosage? So before even, I mean, somebody would be asking me the question, what is the dosage? In wrap, I mean, hot mix recycling designs, we need to know what they want. What is the kind of wrap, what is the binder's spec? I mean, binder's penetration. So based on only the dosages will be decided. There is no general specific, like this is the dosage it will work with rejuvenators. Whereas in warm mix, you can say that. So that is the difference here it makes. So warm mix, you can say, okay, the dosage is this much, this is what it will give you, this is workability at so and so dosage. But rejuvenators are a little different. So there is a lot of laboratory work that has to be done here. So similarly, they have a criteria, they defined a criteria where they said, okay, my wrap binder has so and so penetration. Now I need to use a regenerator if my pen is more than this or pen is less than this. So those kinds of data, for example, anything less than 30, you may have to use a regenerator. And then anything less than 30, again, they go again with a subcategory like 20 and 30, and what kind of wrap can be used and things like that. So this is another project which we did in China. So it has, again, AC20 is the grade that they use. Here 40% wrap was used. Since it was 40, again, here it was like a rejuvenator, only the rejuvenator was used here. The paving temperature was typical to hot mix here. So there was no rise in temperature. You can see the production temperature was typically the same hot mix temperature, 155 to 165. And the paving temperature was 155. I mean, it seems little here in our case, usually the paving temperatures are less if our hauling distances are more. Another 140 centimeter treatment with rejuvenator. So here they have used some virgin binders and mixers here. So the idea of, again, the using the regenerator, what I discussed earlier was, we need to see what we want. Like with if I'm getting, so this is a study which shows HMA with 20% wrap was as good as, I mean, like with rejuvenated at 30%. So we can add 10 to 15% of rep. So that is also one thing that many of the projects that they adopt. So typically they have a clause where they use a wrap. So that is again a clause or a limitations on how much of wrap can be used. But to fully utilize that, you need to know whether I could get those properties if I use the maximum amount of wrap. And if you couldn't get it, then what can be done? I mean, to get it in a different, I mean, easy perspective, if you don't get the bearing capacity of a soil, we add an additive. As simple as that. That's how their design works. So again, few more studies with rejuvenator at different dosages. This was again the performance grades. So you can see the modulus, how it changes. So basically they were more stiff, and we typically try to get somewhat more flexible ranges for those binders, for those wrap binders. Again, few more with different dosages on rutting. And here you can see we have the first few is related to only with the rejuvenator, and then we have only a warm mix, and the next two what you see is that a combination of warm mix and rejuvenator. So this is very interesting as of now. So they want to fix these combinations. Various studies are going on this perspective. Again, cracking is a major thing that they are more bothered at low temperatures and especially cold weather countries. So a few more studies and data on those. So there is a project that we did in North Carolina. Again, this is a combination of warm mix and different rejuvenators. You add different rejuvenators and see what happens at different dosages. And typically the idea is to see how uniform the mix is in the plant. The only thing what you can see is how uniform the mix is. And then while laying, you look at there is also non-destructive testing kind of density checks that we do after every passing of the compaction, the rollers and things like that. Typically, this is one good thing which shows how much of wrap you can use in field. So in a hot mix, we have 7 to 8 passes to get your compaction. So if you look at IRC, I think it's 119, or you follow the orange book, it says you need to achieve 92% of your maximum density. So to achieve that, typically we in India adopt around 6 to 7 passes with 2 high vibratory rollers, with few normal rollers, and then finally one pneumatic roller. So when you go with wrap, this doesn't happen, and you may typically end up using more passes. So when you start using more passes, what typically happens in the field is these aggregates get crushed. So there is an optimizing even in number of passes. If anything goes beyond 7, 8 passes, you are in fact damaging the whole aggregate structure of the skeleton. So even a core taken after 10, 15 passes will not typically represent the Marshall mode that we are making in the lab, because aggregates are crushed and you'll find more fines in that. So if I want to finish it that 7th thing, I need a better workability. I need a better binder, a little binder which is more ductile. And hence those criteria decide how much of the dosage these products are used. Again, another project with different combinations. These are the properties again using with warm mix and warm mix plus rejuvenator. I'll be sharing this. I mean, these numbers are, again, it will be a repetition of those tests. So the modulus values, your typical dynamic modulus that we do against control sessions. Red depths. So overlay test is typically, that is very common there, that they call this the Texas overlay tester. So they want to see the number of cycles of failure. They create a small fracture in the sample and they keep testing it and how long it takes. So typically hot recycling mixes are usually tested against fatigue failures, cracking and things like that. Not more on rutting. So typically if you look at rutting perspective, they may or may not, mostly may perform better on the rutting perspective. And that is why when we I mean, again, I don't want to get into the balance-based design or ideal CT test kind of a thing. I think they would have already covered, many of the people have covered it. And our objective is to tell that you get a rutting values may be a little less than what you compare to the typical wrap. But again, it may crack at 0. So we are trying to find out a range where you pass your fatigue failure as well as the rutting criteria. So this is again based on the DC test. This is again disk compaction. It's again a fracture test. They're typically used to understand the fracture energy required for cracking and things like that. So there is again, this one is a comparison between two different grades of PG64 with different kinds of wrap system. So the temperature was in Fahrenheit, so I'm sorry for that. So here the mix was prepared and it took almost 45 minutes to haul it in the sense from the plant to the site. Two different tests were done, like one with a control mix with warm mix alone and another one with warm mix and a rejuvenator. The asphalt was 5% with somewhat like the total asphalt content, which is like the virgin asphalt was 3.2% plus 1.8 was from the wrap. That is how the calculation was done. And the properties were tested. You can see some of the properties here. Typically, again, the temperatures, the low temperature, cracking, etc. This is again the direct compaction tension test. So more or less the model is similar, but we could see a little bit of difference in that. This was done at almost at a sub-zero condition, -6 degrees. And again at Kansas, two different grades, like one performance grade at a higher stiffness and one with a lower stiffness, with two different, with the same wrap content. So you can see the difference between two. Again, this was same. The dosage of the rejuvenators and the EVO, the warm mix was similar, but with two different grades of wrap binders. This is how the difference we could see in the cycles to failure. Again, a strain level test. You can see that here the PG64 has a much bigger strain levels. Again, the mixes were same. Here we want to just show that has a higher cycles to failure because of the higher grades of bitumen, but the dosages and everything was kept similar here. I think I can share those slides. These projects are, these are glimpse. Some of the projects only I could cover it here. So to conclude, one thing is, this was a statement which I took it from this article. So more than 19% of asphalt pavement material removed from road and parking lots in 2017 was put into productive use. So this was the data of 2017. And today, and this is data typically only for US, not for any other place. And the use of wrap alone has resulted in cost savings of, they have a kind of a calculator that they use to find out how much of virgin aggregates have been replaced by recycled materials. So this is the value that they are seeing. So the time once we start seeing these values, I think there is a lot of potential to start exploring to use high wrap into the road system. And in fact, there were a few years back where we have seen the wrap being dumped into the subgrade layers, and not the subgrade exactly, the granular base layer where the wrap have been used. But as on today, we see most of the wrap goes into the DBM, and most of the other bituminous layers may not be on the top surface, but we could see that. Mainly the challenges what they see with this, the current specifications, what to follow, how much to use, what is the dosage, what I need to adopt, what kind of mix designs I should use. So these are areas which are still open to study. In fact, we talked about the particle clustering. So that itself is a big scope for what wrap analysis needs to be done, how it has to be done. And wrap in BC layer is still new. We have not done anything on that. And one of the areas where we recently, the last 2 years, what we saw, one of the interesting thing is wrap being used in cold mixes. Like you take the finer part of the wrap. So once you start generating more wrap, you segregate it, you do all the, the fractionations, everything. So many times happens is that one fractionation is not used and the remaining fractions are used. So what do we do with that? And there are many applications in not only in hot mix as well as cold mix, where you will use uniform graded aggregates, single graded sized aggregates. So those applications, whether these wraps can be used, nobody has used till now, because those, like I would say pre-mix carpet, slurry seal, microsurfacing, nobody has used wrap in all those applications. So that is where all of a sudden there is an interest where whether we can use these wraps. So there are some areas where, there is a lot of scope to do work. In fact, we are also working on many of those such things. I covered, I hope Yeah. Thanks.
Now the floor is open for queries. Participants are either requested to turn their cameras on and ask the questions, or you can post the questions in the chat box. So the first question is from Ujjwal. In case of recycling, hot mixing, wrap mixing at HMA plant, please suggest how is it possible to add wrap in batch mix plant? In the area where wrap adding is not in practice, how a contractor would be ready and accept such a work? Is there any policy in our country?
Okay, good question. The thing is, as of now, there is no policy. There is policy, but it is different. So the policy says you can use maximum 20% of wrap. Now, how we are going to use it is up to the plant and the contractor. So half of your question is covered. I mean, so there is no way, nobody says how you are going to add it. Now, going to a batch plant, you are asking. So our experience, what we have seen is the existing or the conventional batch plant, there is no way, except that you need to do a modification. So if you are going to talk only from a plant perspective, yes, you need to modify your plant. Or the other way is, if you are having 4 bins and only you have 3 gradations, use the 4th bin for your wrap feeding. Now, you can ask me another question. Okay, I have fitted the wrap. Now you are going to heat it or not? Okay, if you want to heat it, then again, it's not possible in that conventional mix plant, hot batch mix plant. You need a conveyor belt and you need a heater. So this has to be done at the plant. There is a modification that is required. As of now, there is no specification for a plant as such, but there are companies which are making such plants in India. Did I answer the question?
Yes, sir. Yes. Yes, sir. Thank you.
The next question is, can you please discuss on the policy decisions regarding wrap usage in other countries?
Okay. For other countries, I mean, one of the things in US, what happens is it is mostly state oriented. So every state has their own kind of specifications. I don't have access to all, but some of them we can, maybe in a later slide we can share it. I don't have it currently. Some of them allow. For example, there is a limit 40% in BC. So, I mean, sorry, in the bottom layers. Even they are allowing in BCs nowadays. And they have a quality constraints. So for example, again, there is the same criteria that have already decided. Like, okay, I need to have this much of pen on the residual binder. So those kinds of specifications do exist there. And one of the advantages there, you approach state-wise, so it is easy to get the approvals. And then we have this already, I mean, they have certain, this association, especially the ARRA, is one thing which is accepted over the US and many other countries. I think you would have gone through this. I mean, I do have a map, sorry. Okay, I can show you this. This is one thing which many of the people are adapting. This manual. So this quietly used for all the hot mix protocols, whatever they want to use, not from the mix perspective, but from the plant and production and using facilities. So this is one thing is quite widely accepted there. Okay. Sir, rash is reclaimed asphalt. I mean, can I take the next question? If
Yes,
there
sir.
are few questions before that.
okay. Sorry.
So there is a question from Arun Sagar, IIT Palakkad. Are you able to see that?
Yes, sir, it's there.
Sir, I'll read out the question. What was the general issues based on cases where the wrap percent was more than 50%, even with EvoFlex, where the mix was failing based on performance, and was there any field studies?
There are field studies with 50% wrap with EvoFlex. I don't know exactly what failures we saw. I mean, I don't have okay, this was a failure when I used 50% wrap and EvoFlex, but I can tell what challenges typically when we use 50% wrap with, even with the rejuvenator, sometimes we feel. One may be with 50% of wrap and EvoFlex, first we are okay. I mean, the work has been done very well. But when we look at the long-term perspective, we have seen cracks. I mean, the wrap design was done with rejuvenator. So everything properties we could match. And then after 2-3 years or 4 years, we could see cracks. So that was a failure we considering that, okay, initially the properties were right. I mean, from the lab perspective, but on the field, After 3-4 years, if it is cracking, then the regenerator, or even, I mean, either way, I don't know, I don't put it that way. But yes, the regeneration has to be completely different. I mean, we should have done a much better mix design or something on that. Or a long-term study still doesn't, I mean, we don't have enough data to prove even rejuvenators on the long-term basis. So we have done, for example, there may be, we have some roads in US which was done with hot mix recycling 10 years back or 15 years back. So that is why we are able to see these failures. So that is one thing where we want to study. So those kinds of roads we don't have as of now here. But that was one failure. When we go up to 50%, we could see long-term failures much earlier, like within 3-4 years, we could see some cracks. I will check for any field studies. As of now, I don't have anything with me now. I can revert back with the team.
Okay, sir. The next question is, please guide and share your experience of using RAP in BC layer. Is there any issues relating to performance? Is there any such requirement to provide another layer on RAP mix like seal coat of 12 mm? And what is RAS?
Experiences, I mean, as a company, we have done a lot of work in abroad, but India, we have not done with BC. And even if some of the projects, what I am aware of, that has been done with BC doesn't has more RAP, 15 to 20% max, I that too on a trial kind of a thing, not on a large scale. So commenting on it, on that, what kind of challenges or failures we have seen, it's very difficult as of now. BC layers at 20-30% abroad, what we have seen, we have not seen any challenges. Again, coming back to that, there also in BC layers, it is limited. They have not gone much beyond 50 or 40 or something like that. So DBM, they have gone much. BC is still around 30, 20 and things like that. See, that is what, I mean, that's a kind of thing which currently people are just pushing the limits. So once we go beyond that, we will definitely see challenges. So if you look at, there may be a few examples here and there. That is one thing. And I want to understand why, I mean, on what basis that, I'm sorry if I am not able to understand, like seal coat of 12 mm. Why we should need seal coat is my question. I mean, I'm just questioning the question.
To cover the rep mixer.
No, I mean, why do you feel the RAP mix has to be covered? I mean, is it because you feel there will have more voids?
Maybe I don't know. I have not experienced. That's why I'm asking.
No, in hot mix, it looks same. I mean, you have a DBM BC, so your BC has the same gradation. Whether you use high RAP or low RAP, you need to meet the gradation. So your top layers have to have the perfect finish. So for a BC, nobody is going to do a seal coat. So it is not required. If you ask me, are you asking about a hot mix recycling BC? If to 20% RAP was used in a BC, do I need a seal coat? No. But if you are using a cold recycling or something that maybe a seal coat, or maybe in that for a hot mix on a BC with a RAP, no, I don't think there is a seal coat is required.
Okay. Good. Thank you.
In fact, you don't need a seal coat. That's what I would say on a BC layer.
Okay.
Sir, what is RAS?
Okay, reclaimed asphalt shingles. Okay, this is a kind which we are not used to. These are asphalts that are used in the roofing. There is a lot of asphalt that goes into the roofing in US and things like that. So they get exposed to a lot of high temperatures and things like that. And those are again reclaimed, and there is a big inventory of that lying over there. I mean, that is also goes into the what we call here RAP mixes for roads. They use RAP as well as RAS. They are also as similar to your aggregates, either that they are shingles actually. I don't have the exact, sir, I don't have the exact spec of the RAS with me.
Okay, so I can just quickly add, because the participants here may not know really what is RAS. So this is, you can call it as a roofing asphalt. Roofing asphalt, fine aggregate particles, and the binder, if I want to speak in terms of penetration, you are looking at 15 or 20 pen. So that hard material. And there is a big incentive, like what Dr. Asif says, to use that material in the recycling. So many studies in the US have used a combination of RAP as well as RAS. So since in your slides you mentioned RAS, I just thought the participants should know it.
Yeah, so they produce, I mean, yeah, so they have a lot of, I mean, like the amount of inventory that they are creating with RAP, they are creating as much as with the shingles also. So they have to be used and they get credits for that. Thanks.
Okay, so how can we check the absorption of moisture by the wrap material at micro level, maybe at laboratory
Fatima, you
level?
missed Josina's question.
Yeah.
Oh, sorry, sir. Okay.
No problem.
Sir, shouldn't
Go
we
ahead.
check the quality of aggregates in wrap before taking it to test? Also, shouldn't we preheat the wrap to remove moisture, even if it's having less percentage of wrap?
Yes, we need to check the quality of aggregates. Any aggregate we need to check, but what qualities we are talking about is that is here the question is. So your wrap has one is it's they are already coated aggregates. So if you are they are coated black aggregates for me. So when we use it in hot mix, we consider that the binder will be used for if why because I need to mention here that if you are considering it as cold mix, we just consider it as a black piece of rock. But when we are talking about hot mix, yes, we need to use the binder. So the aggregate, the properties matters to us. Now, should we preheat the wrap to remove moisture? How much of moisture is there would be the first question. So if your moisture is less, when I say less, 2%, 3%, we will not preferably heat it. I'll tell you the reason being that if it is cold feeded, again, we may have to heat it, but usually in a preheating drum or when it goes into a hot mix recycling specifically, this water is nothing. I mean, the temperature at which they are facing, it will not create much of a problem. Again, I mean, these are all questions. I mean, there is no abstract answers because I may tell an answer and I may have to again refute myself here, saying that, okay, now we are going to use 30-40% wrap. Yeah, there will be too much of moisture. So that much of heating I may have to give. Okay. Another answer would be that in a plant, when we use, we maintain the temperature based on the burner opening. So this we have done, in fact, in India itself, somewhere we have tried this. So if we have a moisture in the wrap, what we do is we expose that aggregate for a, instead of, so my burner opening is usually 17 seconds. We just turn it to 19 seconds. So this is out of only a trial error and then the practical experience we have done this. I don't have any, I mean, like a specification for this, but this is how we typically address the problem at site.
Asif, if you don't mind, can I add few things here?
Sure, sir.
Okay. So this is Murli Krishnan. I'm sorry, I'm not able to switch on the video here. I think for the last 3-4 days, we have been hearing the same questions about the quality of the aggregate in the wrap. And I think Professor Sudhakar Reddy also very clearly mentioned, he gave exactly the same answer Dr. Asif gave. What is the quality that you are trying to look at? As of now, there is no test or anything that is available to check the quality of the wrap aggregate. Please remember that this wrap material was once used in a bituminous layer. Okay. Now, when you do a rigorous mix design, and if you come to IIT Madras, we will show you. In fact, Tushara can also share something with you. So we do some gradation analysis, what we really call as white gradation or black gradation. Okay, we take the wrap, burn it in the NCAT oven, and we find out what is the white gradation, and then we do the black gradation. So that is, so there is, as of now, there is nothing like specifications for wrap aggregate, because our main idea is to use as much as possible into the mix.
Yeah.
The second thing that I just want to add to what Dr. Asif already said is, we did a lot of mix design, wrap, hot mix design for many industry here, like many projects. And most of the time what they do is the final mix that comes out has to be or have the temperature of 160, 170 degrees centigrade. Now you need to understand, if your wrap is being introduced cold feed, then you need to balance your aggregate, the virgin aggregate that you add. And I have seen it by myself. Sometimes they superheat the aggregates. It goes more than 200 degrees centigrade or 220. There is basically no control. It is only the opening. You open it for 10 seconds, 20 seconds, 30 seconds. It is chaos there completely. So if you are really talking about the amount of moisture that is present, it just is immaterial. But if you are really talking about cold mix, you don't need to care, because anyway we are adding water. Okay, I just thought I should add that information. Thanks, Asif.
Thank you.
Thank you, sir. Before going on to the next question, I would like to remind the participants to fill the feedback form shared in the chat room. The next question is, How can we check the absorption of moisture by the wrap material at micro level, maybe at laboratory level? Because at the site, the wrap is stockpiled in large quantities. The exposure of the material at site to the environment is different from what we can find from laboratory level. As you said, this may be one of the factors to decide within what time the wrap has to be recycled from the date it is milled.
Yeah, so that is one thing. So if we typically you store the wrap for a long time and it gets exposed to it, it absorbs moisture to a certain extent. Again, I mean, what we discussed previously, I think most of I mean, that is the same thing. I would say that it depends what sir said, and on the field, this is the only thing that we can do. I mean, if it absorbs the moisture, how much of moisture is that? And if it is cold feed, then it is different. If it is hot recycling, then we heat it to a certain extent at 160, 180. Typically, this moisture goes away. But again, this challenge is there. You keep the opening of the burner at too little extent, you burn the aggregate, in fact. For field, there is no specific for the laboratory study on the moisture. I don't know what specification exactly, the number I don't remember, or I'm not sure if sir, is there any specific? I'm not sure on the laboratory side what.
No, nothing like that. Nothing.
Maybe
like
you can just put it in oven, take a dry weight and then wet weight.
So say, whenever you are talking about hot mix recycling, you know this increased emphasis on moisture that is being repeatedly asked here, it just is immaterial.
Okay,
because
but
anyway, yeah.
So can I add something here?
Yeah.
Okay, our one personal experience on this, I'm saying this is only purely from the Ingevity perspective. So the warm mix what we are using has a very good moisture susceptible properties. So typically those warm mixes, even there is a moisture, we have not seen any problem. Typically, that was in fact when warm mix was developed in US, there was a criteria. In fact, these kinds of interesting to know that these questions are coming now. When US started using warm mixes, same kind of questions came up saying that, okay, now I'm going to reduce my temperature. If there is moisture in the aggregate, what will we do? I'm not talking about hot mix recycling alone. Even in normal hot without recycling, there was the same questions that started coming, like what you are going to reduce the temperature by 30-50 degree when you are using warm mix. So if there will be a little bit of moisture still there, what will they have? The moisture will have problem. Then it was a unanimous call that any warm mix agent that is being developed should be moisture susceptible and it should have moisture resistant properties. It should meet criteria such as T283, Astro 283 and things like that. So if you are going to ask me, well, this there is another way of answering it. If then there is a little bit of moisture, when you use chemical additives, typically it doesn't affect anything. That is taken care of. In fact, many cases that has been that is how it is.
Okay, sir. So could you please explain the process of adding rejuvenator to wrap? Is it directly added? Also, should we heat wrap and rejuvenator together?
Okay, so there are various methods again here. Two, three methods are available based on the conditions. I mean, it is again project to project, it is different. Some of the rejuvenators are added to the virgin binder. One simple thing. I mean, it is not the all cases. Some are added at the mixing places where your wrap is getting blended with the binder and the virgin aggregate. So there are 2-3 ways. That is again so product specific. That is how it is. But typically on a plant, in a lab, typically I think if in a laboratory perspective, you typically add in the virgin binder. Most of the cases. There is also, we have this flow meter kind of a setup to dose it. Exactly at which point you want to dose it. Those facilities are there where a lot of wrap is being used.
Sir, will there be any increase in the quality of wrap if we cold mill it?
Sorry, I can. Will there, hello? What was the question?
Will there be any increase in the quality of wrap if we cold mill it?
Quality of wrap. Okay, instead of heating and milling it, you're asking whether if it is just cold milled.
Yes, sir. Yes, sir. Yes, sir. That is the question.
There may be a difference. We have, I mean, I'm just answering from a different practical perspective here. Thing is, In hot mix, some of the binder you are just, you are melting some of the binders and then removing. So you may get the aggregates more or less, it won't be crushed here. In cold mix, it may be crushed again. I don't see a big difference. First of all, that. And second thing is, when you are going to fractionate it and do a lot of other things to it, those impacts will be nullified here. When the final stage, it will be not impacting much. If you are going to do a in plant hot mix recycling. Except for that, you will be, what you say, it is the binder may be the melted out. So you will get some of the pieces as such, the aggregate coming out. Here you may be breaking some aggregates in the cold mixes. Even in hot, even when it is heated, it will break some of those things. You can't avoid that. And cold and hot, you said it is more to do with the kind of the blades that they put in. Actually, that is how most of the wrap, what we want is modified based on the kind of milling mills that we call it as, we have different kinds of blades for that. So that defines what kind of output I want more than this. And hot is mostly used in your in place, not for plant recycling.
Sir, the next question is there any chance the wrap aggregate loses its abrasion strength or any other strength? If yes, can that wrap be used?
No, I didn't get it. Abrasion strength. Again, you want to know, again, this is related to the quality what you're asking. So the wrap has a binder on that. So you are going to test with the binder, the abrasion value, or you are going to remove the binder and test the abrasion value. So when you get a wrap, you are getting a wrap with the binder, right?
Yeah, yes, sir. But for research purpose, we may be doing, we may extract it and try it, right?
So extract, so once you remove the binder completely, and now you are going to test the aggregate, right?
Yes. At that time, if let's say the abrasion value is beyond the limit, let's say.
The previous road I already used a bad aggregate, you mean?
I don't know if.
No, I'm sorry to ask that. If when you say if it fails the abrasion value, means already there was a road which has used those aggregate, right?
Yes, sir. But is there any chance, like right now said, because of this hot
My
HIR
honest answer,
chance?
nobody has done this study. I don't think somebody has removed the wrap and checked whether the abrasion value of the old rock was good enough.
Yeah. Okay.
We have not done that, in fact.
Okay, thank you.
Next question is, could you please explain on how long can the binder treated with rejuvenating agents be stockpiled before becoming ineffective? And also, what is the expected life of the rejuvenated surface?
Okay. So first thing is, how long can the binder treated with rejuvenated agent be stockpiled? So that I told you last, in fact, I mentioned that, first of all, are we going to add the rejuvenator in the binder? Where I'm going to add is going to different. Your question is specific only if I add it into the binder, right? See, in the binder, when you add it, again, it is designed. If it is, will you keep the binder hot or will you allow it to cool down? That is the first thing. If you are going to use it immediately, no problem. Stockpiling, also no problem. But while stockpiling, how many times you are going to heat and reheat and things like that? This is again product specific. Some of the products you can heat it twice. Some you can you may heat it to three or four times. Some products it is better to use it as and when you add it. Here, because regenerating agent is added when the binder is hot. You can't. It will be added mostly at 150, 160 degree when the binder is at 150 or 160. So you can't. You allow it to cool. It's okay. You can store it. Provided how you are going to cool it. Now your question has. I'm a little concerned. You are stockpiling. See, once you have used the regenerator in the binder or the mix, you use it, right? You won't use the regenerator in the binder, and binder nobody stockpiles. Binder is in the truck. So when you talk about stockpiling is about the aggregates. I just want to understand what you mean by stockpiling. So your stock, if you are talking about a mix, if it cools down, then how will we lay? If you are stockpiling, if you're talking about aggregate, binder, regenerator, everything put together, that is a stock. And if we pile it, we can't, I mean, like you have to reheat it again.
Asif, maybe she is talking about or thinking in terms of a cold mix wherein
Yeah, that's what I said. So in cold mix, I don't need a rejuvenator.
you don't need a rejuvenator. You can add your emulsion and all those things and stockpile. There is no problem.
Yes, sir. Even in emulsion, if it breaks, we can't stockpile it, because at least in hot mix you can reheat it. In cold mix, we can't.
You cannot. No.
Yeah, we cannot do that.
No, in the shorter run, you are laying your road and then you just want to create some places. So that's what it is.
Yes. Yes, sir. In short run, yes, sir, we can do that. And in fact, I think maybe stockpiling, if it is shorter run, yes, we can do that. Again, the stockpiling can be done provided you lay it within the prescribed temperatures, because after that compaction is an issue. So rejuvenator effectiveness is one thing. That is true. And one more thing, this question may be more effective if it is talking about warm mix. Here, rejuvenator is to give, changing the properties of the binder. So that is completely different. And expected life of regenerated surface. That's what I said. I mean, we expect a typical expectation is that you don't have cracks or rutting anything for 5-7 years. So rejuvenated surface should be as good as your hot mix. So that is the idea of adding rejuvenator. When you do a hot mix, whatever is your expectation, we need to achieve the same thing with the wrap and the hard binder. So expected life of a rejuvenated surface is what I would be getting if I use 100% hot mix. This is the criteria for everywhere. I mean, I think that's a universal concept. I'm sorry, did I answer the question?
Yeah, I think it was fine.
Yeah, yes, sir. Thank you.
Okay.
Okay, then the next question is from Josina. Sir, how much is the blending time of rejuvenator and wrap in general?
Okay, this is again specific to product. Okay, if you are putting it in binder, usually blending more than time, how do you blend it is more important. If you are you're using it in, I'm thinking taking two examples I'll give you. One is if I'm using it in virgin binder. If you have an agitator, you agitate for 20 minutes. Typically, I'm saying this is again, I can't take for every, it's case to case, it changes. 20 to 30 minutes should be fine for most of the rejuvenators. 20 to 30, I'm just taking a very, very general case. And if I don't have an agitator, what I do is we typically add it in the binder truck and then transfer the whole thing into a plant. So that solves, there is no time here. It is only a time to get it mixed well. So that is not time dependent. It is more of this one. Now going into any other place, for example, I'm feeding time into the pug mill, wherever I'm feeding it. That is again, it depends on the temperature of what I'm doing. What is the quality of wrap? First of all, we need to know how hard the wrap is. For a fresh wrap, I don't think it will be a matter of seconds or few things. So your wrap will decide if it is going to be feeded somewhere other than the virgin binder.
Thank you, sir. The next question is from session 1. For session 1, is there any way to characterize the wrap binder from the wrap mix without extraction?
No, I don't know any. If anybody else have an answer, I would like to have. I would also like to know.
No,
Can I just go, Neethu Roy, if you don't mind, can I give a tongue-in-cheek answer?
Yes, sir, yes.
Okay, so you have to just take it in what you can say in a very lighter manner and not take it very, very seriously. How can you even find out what is there in it without even extracting it? Is this a Chinese puzzle that you are looking at? Okay, here is this box. Say some magic wand and then say what is there in it, tell me. So this is something similar to one of my friend in state highway agency asking me, I don't know whether she is here, given a binder, can you find out what is its age, where it came from? And then I replied back to her saying that, okay, I give you a marine clay. Can you please tell me from where in India it was dug, what was its age, and which depth it was taken? Okay, so I don't really think these kind of questions can be answered.
So I just want to ask, like, is there any particular context that in which you are asking this question, or like, is it related to any other test or anything else that you have linked based on which you are asking this question?
No, madam. Actually, I just want to know because extraction of a wrap binder involves time and money. So by eliminating this, can we eliminate this by just with the mixture? Is there any way to find the
why extraction of the binder from the mixture cost money and time? I don't understand. I don't think it cost anything or anything. At the laboratory scale, yes, it is a tedious process, but if you are really interested in pushing back as much of the constructed material into the recycling aspect, the amount of resources and money that we save in this whole exercise outweighs some of these small things. And in fact, there are many equipments that are available. If you are still thinking in terms of a centrifuge and a rotary evaporator, then we are long way, but there are many equipments that are available, what are called the asphalt analyzer, in which you just dump your ramp and start the machine. In one side you get the bitumen, in another side you get the solvent, in another place you get your aggregate. And these are all fairly automated, standardized, and in fact they work without harming the individuals operators who are doing it. And if I am may be permitted to say so, I have seen in many engineering colleges, even in highway agencies, contractor site, people using benzene, trichloroethylene without even having any protection. These are all cancerous material. They have to be used with adequate care. At least the safest solvent as of now I can say is use N-propyl bromide or something. Maybe Asif can add something more to it. But if you really want to know the quality of the binder, you need to pull it out. There is no other way of doing a voodoo magic on this material. Already the material is fairly complex.
So you just such Asha Lata here. So you're mentioning that now the equipments are there, where from one side you get the binder, the other from aggregate and the solvent. So like those are available in academic.
Yes.
Academic.
Yeah,
okay. Oh, I see.
How much
does it cost? How much does it cost?
Well, they cost a lot, but it all depends on. But if you are ready to spend 15 crores per kilometer, would you mind paying 30 lakhs for equipment?
Okay. That's a good
No.
question.
See, in fact, I will insist that every highway laboratory should have some kind of equipment like that, because I have seen many labs in which students use these solvents which are carcinogenic in nature without being told that these are carcinogenic. Okay, so these equipments are European Union standard. So basically you can process flat 5 kg of material within 1.5 hours. The whole binder, aggregate, as well as the solvent used is separated out in no time. I can send you a link also. Okay, but at the same time, you can be safe also. It is safety. That is the most important thing. See, that is why I get really aggrieved when I see in some places a student running this without even wearing a mask, without even covering the upper portion of the body, and exposing themselves to such solvents without this working in a fume hood. These are carcinogenic.
So those working in this sector as well as the researchers should be made well aware of this impact of this.
They have to work always within a fume hood. Everything should be in a, you need to have that proper exhaust. The lab should be ventilated. Only then you should use it. Otherwise, you should never use this. Asif, you want to add something here about the safety aspects?
Sir, I mean, as you said, I mean, those solvents that have been used here has been long been banned in many of the countries. And I think it's a good step that you said this, because many of the people are not even aware of it. I have nothing more to add, but just to acknowledge what is happening here.
Yeah, in fact, any other country other than India, if you try to get benzene, trichloroethylene, or any of these things, you will not be able to get it.
They won't even.
Yeah, they are carcinogenic. You will be, in fact, if you try to use any of the solvent in any US laboratory, they will put you in jail.
No, there is not even these kinds of labs doesn't have it. In fact, I have been to our labs many times. They don't even talk about it.
They don't even talk about it. And in fact, if you enter any asphalt lab in this country, be it industry or contractor, unfortunately, even in some universities, you smell this solvent. And then, you get repelled the way in which young students are exposed to this, with the faculty members not even telling them that this is carcinogenic, probably because they don't even know that. You need to be extremely careful in using all this things.
I think, sir, it's ignorance, probably, because
I am sorry, ma'am. I will never allow any of my young students to go anywhere near it. They are carcinogenic. You understand when I say carcinogenic? What
yeah,
I mean?
I understood.
Yeah.
Thank you, sir. Hoping there are
Zarina, you are not audible.
Sorry, ma'am. Hoping there are no more queries, I would like to request Dr. Kavita, Associate Professor, DKM College of Engineering, Kollam, to thank Dr. Asif Ahmed.
Kavita.
Sorry, ma'am, my net was some issue. Okay. Hope I am audible. On behalf of organizers of FDP and all the participants here, I extend a hearty vote of thanks to our resource person, Dr. Asif Ahmed from Ingevity, for sparing time from his busiest schedule to grace this occasion. It was the best lecture that you have delivered to we participants. Your presentation is well planned and very precise. We could understand more about Evotherm, my new generation Warmix asphalt chemical additive, and also Evoflex rejuvenator. The lecture is truly thought-provoking, highlighting its practical implications. Your presentation skills made it so lively with catchy slides to the audience in and held their attention for 1 hour. So both sessions of today were highly informative, and the complex concepts were presented in a very simple and comprehensive manner. So on behalf of organizers of the FDP and the participants here, I express my heartfelt thanks to Dr. Asif Ahmed and to Dr. Neethu Roy. And I also want to thank the organizers of this FDP, Dr. Ashalata ma'am and Professor Trishara, for selecting these eminent personalities, and also our Professor Dr. Murali Krishnan sir for being the pillar of support of this FDP and sharing your knowledge and experience. We are so humbled, sir, for you being here and translating our silly questions to the resource person. Thank you very much, sir. I thank all the participants for being here and actively participating in both the sessions today. Thank you. Good night to all of you.
Thank you for the feedback. Thank you.
Thank you. Thank you, Murli sir, Asif, and Neethu for your valuable presentation, and Murli sir for all the wisdom you are given to the participants as well as to us. Thank you.
No wisdom, common sense, ma'am.
Okay. Thank you.
Thank you, ma'am. Thank you, Kavita. Thank you, ma'am. Thank you. Good night, ma'am.
Thanks.